Good day, everyone. We're reviewing Wetzel's Limnology textbook. This is edition number 4, and we're in chapter 7, which is the fate of heat. And more specifically today, we'll be looking at heat budgets and measures of stratification and mixing. Heat budgets can be computed within lakes to assess whether the heating and cooling expected from the surface energy budget are in balance with changes within the lake. When they are out of balance, other processes may be contributing, such as advection. Heat content, H in joules, is a function of the mass, M in kilogram, of the substance temperature, T in degree centigrade, and C PW, the specific heat capacity of water. Then, heat flux, QT, in a layer of thickness delta Z, that is the change in heat content over the time delta T in a layer, can be computed from time series measurements of temperature using the following equation. So equation number 7-9. Where T temperature, T1 and T2 are times 1 and 2 respectively, such as delta T is the time the difference between them, ZC is the measurement's depth, delta Z is the depth interval above and below ZC prime, and rho is density in kilogram per meter cube. To obtain the change in heat content for the full lake, heat flux in each layer is summed, accounting for the volume of each layer. The relations between depth, area, and volume are obtained from a hypsographic curve. Change in temperature is calculated as the inverse of equation 7-9, where delta T is equal to QT by over rho CPW by L over delta T, where L is a vertical dimension. The historical work on this problem, known as Bergian heat budget, addressed changes in heat content over the summer, beginning with temperature at 4 degrees centigrade over the winter, beginning with minimum temperatures up to 4 degrees centigrade, and over an annual cycle from the time when temperatures were minimal to the time when heat content was maximal. In contemporary analysis, heat budgets are used for further understanding of a lake's hydrodynamics. They can be used to infer the extent of turbulence and mixing in the thermocline and below. By comparing changes in heat content within a lake to the surface energy budget, advection can be assessed, that is, changes in heat from incoming snowmelt, rain, streams, or rivers, or from transport elsewhere in a lake. Additionally, heat budgets can be used to determine if changes in heat content at specific depths in ice-covered lakes are due to either direct solar heating or mixing, and to validate fluxes with eddy covariance systems. Comparison of one-dimensional heat budget from multiple sites within a lake can be used to quantify the flow of heat from one region to another due to changes in wind stress or to differential heating and cooling. Thus, heat budgets are valuable tools for assessing physical processes occurring in lakes. Efforts to quantify the work required to fully mix a lake, that is, a lake stability, began with Berge in 1916 with the calculation related to heat budgets. Stability per unit area of a lake is the quantity of work or mechanical energy required to mix the entire volume of water to a uniform temperature without addition or subtraction of heat. The term is Schmidt stability, and seasonal changes are generally determined based on changing in ST from the time of minimum heat content to the time of maximum heat content, following this equation, where A0 and AZ are surface area and area at depth Z. G is gravity. ZG is the depth of the center of gravity when the lake is completely mixed, i.e. the depth where the mean value of density would be located if the lake was unstratified, also known as the center of volume. Zm is the maximum depth of the lake. Rho bar and rho Z are the mean density and the density at depth Z, respectively. The calculation determines the amount of work to mix the lake completely. Work equals force times distance. The force G, rho Z minus rho average by AZ dZ in each volume element is multiplied by the distance away from the center of volume, Z minus ZG. These products are summed from the surface to the maximum depth of the lake. The unit is joules per square meters. Schmidt stability is scale dependent, and larger, deeper lakes will have larger ST after controlling for climate and altitude. So here, ST is equal to G over A0, the integral of 0 to Zm of Z minus Zg by rho z minus the rho average by Az over dz. Density stratification is quantified by the square of the buoyancy frequency, also known as Brunt-Wetzel frequency, where N2 is equal to minus g over rho over delta g over dz divided by rho. And g is gravity, rho is density, and z is depth. In this metric, stability varies with depth and will be highest where density gradients are largest, as at diurnal or seasonal thermoclines or chemoclines, where density increases due to increases in solutes. When density is only a function of temperature and temperatures are above 4 degrees centigrade, the density profile is approximately the mirror image of the temperature profile. As shown in figure 710, increased value of n occur where the density gradients are largest. The units of n are radian per second or cycles per hour, recalling there are 2 pi radians per cycle. So let's look at this a little bit here. Figure 7-10. So profile of A temperature, T black line, and density rho red, showing the diurnal thermocline from near surface warming, the subsurface layer, and the stratification in the upper part of the seasonal thermocline. B, buoyancy frequency, N. So here we have depth on the y-axis, we have temperature on the x-axis, and here we have N, which is the buoyancy frequency, and we have depth. So in red, we have the density. So the density here is rho in kilogram per meter cube. And in black, we have the temperature. So therefore, the density increases with depth. And you can see there's a thermocline right here, and where there's where the density meets actually the temperature. And the temperature, you can see, is decreasing from 32 to 30 degrees, and then decreasing again at about, let's say, like 16 degrees, 17 degrees centigrade. Well, actually, no, sorry, about 29 degrees centigrade, at about 16 meters depth. And so once again, we have the temperature decreasing here, we have the temperature decreasing here, and the temperature being pretty stable during the thermocline. And then the density here, the density increasing, and then stabilizing, and then decreasing again. As for the buoyancy frequency, we have somewhat of a similar pattern. So we have the buoyancy increasing up to this level here, and then decreasing and then stabilizing at about 7 meters, and then increasing again, and then stabilizing and decreasing. So the buoyancy frequency is actually, the curve of it is not mirroring definitely the temperature and or the density frequency on the left. The time series of N in lakes at different latitudes are present in section 2a. Numerous oceanographic studies have shown stratification is weak where N is less than 5 cph, moderate between 5 and 25 cph, and strongly stratified when greater than 25 cph. So let's look at our figure again. So it appears that we have shown that stratification is weak when it's less than 5 cph. So here we probably don't have a lot of stratification in that area here. And then moderate between 5 and 25. So then we're in the moderate zone here and here. And then stratification is pretty high at above 25 cph. So here we have pretty strong stratification. So we have pretty well mixed in this area here, which makes sense because here we have a pretty constant temperature profile. Hence, when with N approaching 30 cph, the diurnal thermocline in Balbina Reservoir at noon in July was strongly stratified. However, values of N within diurnal and seasonal thermoclines in lakes frequently exceed 25 cph. The extent of stratification determines how effective wind or cooling will be in deepening the upper mixed layer or causing mixing in and across the thermocline. The greater the stratification, that is, the larger the values of n, the greater the cooling or wind speed required for mixing. Additionally, the amplitude and other attributes of internal waves depend on n. So when it's highly stratified, so that means when n is large, we need a lot of energy placed upon the lake for that stratification to be changing and for the lake to destratify per se. So here we have, for example, very high stratification in this zone here. So we would need a lot of wind action at the surface to get rid of that stratification, where we have weak stratification in here. Coefficient of eddy diffusivity. Vertical mixing redistributes the heat introduced at a lake surface, as well as at any solutes or particles that are not uniformly distributed. Were it not for the mixing, temperature profiles would follow those of irradiance. Instead, lakes have more complex temperature profiles, as demonstrated by figures 7.1 and 7-2. The downward mixing of heat, the flux F, is conceptualized as the product of a coefficient of eddy diffusivity, Kz, and the temperature gradient, dT over dZ, and including specific heat capacity CPW of 4,184 joule per kilogram per degree centigrade, and density of water rho W. To convert temperature to heat, that is, F is equal to CPW rho Kz dT over dZ. Thus, Kz represents the product of the average size of turbulent eddies multiplied by their average velocity, a concept derived from the kinetic theories of gases. The process is analogous to molecular diffusion, but often several orders of magnitude higher. Mixing BZT below each depth and at each time t can be assessed from changes in heat content over time intervals by removing increases in heat due to solar radiation. Dividing BZT by dt over dz and surface area at each depth and time yields Kz for each depth and time. The heat budget approach provides Kz within the thermocline and hypolimnion as long as there is minimal advection or heating by sediments. The advective effect of internal wave motion is removed by filtering time series of temperature data or by averaging temperature data obtained by profiling at multiple stations. Typical values of Kz determined by the heat budget method, tracer studies, and microstructure profilers are illustrated in figure 7-1. So figure 7-1, the range of values of Kz typically measured in the epilimnion, thermocline, and hypolimnion of lakes. Kz is highest in the epilimnion, where heat loss and wind combine to cause mixing, and least in the more strongly stratified thermocline, Kz. Kz in the hypolimnion is also low, but possibly higher than in the thermocline. Molecular diffusivity of heat is 1.4 by 10 to the minus 7 per meter square per second at 20 degrees C, and sets a lower boundary for calculating Kz using the heat budget method. Kz can also be obtained from tracer studies in which solutes are injected at some depth in the water column. Kz is calculated from their rate of spread. Values of Kz from such studies may include lower values, as the molecular diffusivity of many solutes are approximately 2 orders of magnitude less than that of heat. So epilimnion here, we have Kz's of 10 to the minus 5 to 10 to the minus 2 meters square per second. Thermocline, we have 10 to the minus 7 to 10 to the minus 5 meters square per second. And then hypolimnion, we have about the same than the thermolimnion, but we have a little lower value here, actually a little higher value of 10 to the minus 4 meters square per second. And once again, looking at the definition of Kz, we have Kz is the coefficient of eddy diffusivity right here. Wind-driven mixing in the upper mixed layer. Wind induces near surface current with velocities u, that decrease with distance z from below the air water interface. That is, wind causes shear in the water column, du dz. The currents and the associated shear near surface mixing. The shear stress tau that generates these currents can be quantified by measurements of wind velocities at several heights above a lake, or of flow speeds at several depths within a lake. However, due to considerable experimentation, formulas have been developed enabling calculation from wind speed measured at one height. Tau is equal to rho A CD U to the square, where rho A is the density of air, CD is the drag coefficient at instrument height, and U is the wind speed at instrument height. And then once again, tau is the shear stress. So the shear stress is also expressed as an air friction velocity U star A, which is representative of the rate of increase of winds above the water surface within the atmospheric boundary layer. The boundary layer is the layer within the atmosphere where winds are reduced due to friction. Shear stress is assumed to be equal on both sides of the air-water interface. The equivalent expressions are tau is equal to rho W by U to the square by W, where rho W is the density of water and U star W is the water friction velocity, similar to U star A or U star W. Depends on the change in current speed with the logarithm of distance from the air-water interface. Empirically, derived drag coefficients enable the momentum transfer to the water to be quantified from wind speed. Similarly, these studies provide the transfer coefficient that enable the calculation of latent and sensible heat fluxes. For accurate work on lakes, anemometers need to be within the lower boundary layer, where wind speed increase logarithmically with height above the lake surface. For small lakes, the anemometers are usually 2 to 3 meters above the water surface. By convention, measured wind speed are converted to those at 10 meters, a calculation along with that of the drag coefficient and instrument height, which requires taking into account atmospheric stability. For a neutral atmosphere and light to moderate winds, CD at 10 meters is approximately 0.0013. Values increase at higher winds. The atmosphere is unstable when denser air overlays less dense air, as occurs when air temperatures are colder than surface water temperatures, stable when the density of air progressively decreases above the water surface, or neutral when the density of air does not change with height, at least immediately above the lake surface. Transfer coefficient can be calculated as a function of atmospheric stability using the Monin-Obukhov similarity theory. The stability of the atmosphere influences drag coefficient appreciably when winds are light to moderate. Atmospheric stability over diel cycles and with the passage of cold fronts, particularly over small lakes away from the tropics. The atmosphere is more frequently unstable over tropical lakes. Air temperatures are often warmer than surface water temperatures during the day and cooler at night and during stormy periods over small Arctic lakes. Consequently, atmospheric stability often varies over diel cycles and with the prevalence of cold fronts resulting in considerable variability in drag coefficients as a function of wind speed. For the tropical lake, the air temperatures were nearly always cooler than the surface water temperature, indicating that atmosphere was unstable. For the Arctic lake, for winds of 2 meters per second, CD was 3.6 by 10 to the minus 4 under stable conditions, and 2.6 by 10 to the minus 3 under unstable conditions. The respective shear stress at 0.0014 Newton per meter squared and 0.001 Newton per meter to the minus 2, I guess it's probably not square. Approximately a 7-fold difference. Thus, when the atmosphere is unstable at low wind speed, more shear is generated to mix incoming heat downward and to generate surface waves. For the same wind speed and temperature differences, CD was similar for the tropical lakes and the Arctic lakes. The transfer coefficient used to compute latent and sensible heat fluxes also depend on atmospheric stability and have similar variability, although somewhat larger magnitude than CD at low wind speeds. An implication of this difference is that for the same solar heating, when winds are light and temperatures are similar, the duration of the period of heating can be longer when the atmosphere is stable due to the lower sensible and latent heat fluxes. So before we move on, let's look at the figure 7-12, which graph the drag coefficient at instrument height as a function of wind speed, showing variation with temperature difference between that in the air and surface water for Tule Lake in Alaska in summer 2010 and Balbina Reservoir in Brazil in July 2013, right panel. So this is Tule Lake in Alaska. This is Balbina Reservoir in Brazil. X-axis, the wind speed. CD is the drag coefficient, and it's by 10 to the minus 3. So the values you have to multiply that by 10 to the minus 3 to get the real value of the CD calculated. And here the temperature difference is a proxy for atmospheric stability, with the higher values of CD when atmosphere is unstable, so higher values of CDs when atmosphere is unstable. And the temperature differences that we see, it's really beginning with the most negative green, delta T. So we have then various data acquisition. So this is like for various scenarios with delta T, and then we get a drag coefficient for it. The question often arises as to whether wind or heat loss causes the most mixing in the upper mix layer. This problem is addressed by computing the Monin-Uklof length scale, or LMO, in the water and comparing it with the depth of the actively mixing layer. LMO is equal to U by star 3W over K beta star, where K is 0.41, is the von Karman constant, UW is the water friction velocity, and beta star is the buoyancy flux defined previously. Beta star plus applies to heating and beta star minus to cooling within the actively mixing layer at depth above LMO. Turbulence production by shear exceeds that from beta star minus. Below it, turbulence production by beta star minus dominates. Even the lightest winds, shear production of turbulence dominates that from buoyancy flux near the air-water interface. The sign and magnitude of LMO change over diel cycles and during storms. The ratio of LMO over ZAML indicates the fraction of the mixing layer in which shear predominates over turbulence production. During heating, buoyancy flux contributes to stabilizing the upper water column, such that in a larger fraction of the energy input from the wind is dissipated rather than used for mixing. As in illustrated in sections 2C, when the ratio is small and positive, turbulent eddies are small and more of the incoming heat is stored in a shallow diurnal thermocline. As the ratio exceeds 1, more of the heat is mixed downward. When the ratio is negative, turbulent eddies often extend throughout the actively mixing layer. If winds or buoyancy flux are high enough, as will be discussed below, the actively mixing layer may deepen. Wind-driven mixing across diurnal or seasonal thermoclines, indices that assess whether wind will cause mixing in a stratified lake, incorporate stability either as the density difference across the thermocline or as Schmidt stability. The relevant indices are the Werder-Burn W and lake numbers Ln. Both indices include the effect of stratification across the thermocline and hence the difficulty in causing mixing across it relative to the wind stress which induces mixing. Additionally, they incorporate basin morphometry. Thus, the interpretation of the magnitude of Wn Ln applies to lakes of all sizes. That is, these indices are scale independent. When wind passes over a lake, currents are generated which are proportional to the wind speed. The accumulation of water downwind causes a pressure gradient that depresses the thermocline. As the wind decreases or ceases, the thermocline tilts in the opposite direction, creating a seiche, a basin-scale standing wave along the thermocline, and other types of internal waves. Tilting occurs where stratification is greatest as at diurnal and seasonal thermocline. Shear, du over dz, occurs across the thermocline when shear is sufficiently large relative to stratification. Mixing is induced. Okay. The extent of tilting can be predicted from W and Ln. Similarly, these indices can indicate whether the resultant shear across the thermocline is sufficiently large to overcome stratification and induce mixing. The Vandenberg number is defined as W, and I'll let you read the formula, where G is the gravity, rho 0 is the mean density, delta rho is the density difference across the metalumion, H is the depth of the upper mix layer, U star W is water friction velocity, and computed over from shear stress of the water on the water, and when the atmosphere is neutrally stable, approximately 0.0001 U, and where U is wind speed and L is the length of the lake, or more accurately fetch the maximum length of open water in the direction of the wind. Schmidt stability indicative of the stratification stabilizing the lake at the time of measurements, and shear stress of the surface of the water surface, a function of rho W U star W2 to the power 2, are implicit in the definition of Ln, where St in the numerator and shear stress in the denominator and other terms, and taking into account basin morphometry, higher values of Ln indicate the tilting of the thermocline, and as a result, less shear across it and less mixing. Technically, the definition of the lake number is derived from moments around the center of volume, computed when the wind stress acting to overturn the density structure is in equilibrium with the restoring force. So this is the formula for the lake number. And this is the formula for Zg, which is the height to the center of the volume, okay? So where Z is the depth, Zg is the height to the center of volume of the lake. Zt is the height of the center of the metalumion, Zm is the maximum depth of the lake, Az is area at depth Z, A0 is the surface area, and rho W U star W2 to the power 2 to square is shear stress on the surface. Ln can be readily calculated using lake analyzer. Vandenberg numbers can be obtained similarly, but it's valuable practice to estimate them by examining observational data and using algorithm for density in lake analyzer or other sources. Vandenberg and lake numbers indicate the extent of tilting of the thermocline, that is the amount of up and downwelling induced by wind. So before we move on, let's look quickly at this figure here. Vandenberg number and resulting tilting for the thermocline. For W greater than 10, the thermocline does not tilt. So here we have W greater than 10, the thermocline doesn't tilt. For W between 2 and 10, partial tilting occurs. So partial tilting occur here for W between 2 and 10. For partial tilting occurs, for W is equal to 1, full upwelling occurs. So W is equal to 1, full upwelling occurs, and for W really less than 1, complete mixing occurs. So complete mixing in his. See chapter 8, etc. Okay. As tilting increases, the Richardson number decreases the values less than 0.25, the threshold for shear-induced mixing and the coefficient of eddy diffusivity Kz increases above molecular values, which is for heating 1.4 by 10 to the minus 7 by meter squared by second to the and Ri and Kz are indicative of the extent of mixing due to turbulence. Interpretation for his lake numbers are similar when applied to the seasonal thermocline. All right, so let's move on. Vandenberg indicate the extent of tilting to the thermocline. Okay. So Vandenberg and lake numbers indicate the extent of tilting of the thermocline, that is the amount of up and downwind induced by wind. The degree of tilting in the thermocline is indicative of the amount of mixing that will occur within and across it. Besides the pronounced upwelling when W or Ln approach or drop below 1 and the resultant direct exchanges between the layers in a lake, the tilting induces internal waves that can break near boundaries or in the central portion of a lake. Regression equations have been developed to predict Kz from W and Ln. Because the Vandenberg and lake numbers are scale independent, they can be used to predict the extent of upwelling and downwelling of the thermoclines for lakes of various sizes and shapes. Thus, if W or Ln equals 1 in a 0.01 kilometer square lake, or a 10 kilometer square or a 100 kilometer square lake, full upwelling would be expected in each. Similarly, the mixing associated with the increased shear would presumably be independent of lake size. When diurnal thermoclines are present, their behavior can be decoupled from that of the seasonal one, and it is important to calculate W for the diurnal thermocline based on the density gradient across it and the thickness of the actively mixing layer above it. W would also be computed for the seasonal thermocline and Ln for the lake as a whole. Similarly, for lakes with persistent stratification, meromictic and oligomictic, the Vandenberg number can be calculated for the various layers and the lake number for the lake as a whole. Vandenberg and lake numbers, along with surface energy budgets, are the appropriate metrics to use when addressing whether lakes are mixing in a manner that will redistribute solutes and particulates. Additionally, changes in the magnitude of these indices can indicate whether lake dynamics are changing with ongoing changes in land use or climate change. They can be used to quantify the frequency of events in which dissolved oxygen depletion is alleviated in the lower water column, and along with it, the potential for the release of reduced solutes from lake sediments. When combined with residence time, that is, lake volume divided by the volume of incoming water, they can be used to evaluate the persistence of phytoplankton, including harmful algal species in the euphotic zone. Time series of these values are included in section 2a. And that's going to be it for today. And thank you very much for sticking on with me, and we'll see you tomorrow for processes causing stratification and mixing in the upper mixed layer, chapter 7, the fate of heat, with Wetzel's. Thank you and have a good day. Bye.